my voice is not going to be pretty. Okay, so last time we ended up by this exercise, which created some confusion. We need to design an NFA that accepts all strings and with odd number of ones or zeros, it doesn't matter. Okay, so what I started with is to say, okay, I will assume that I want to end up by 1. So in this case, you do this. So you say 1, 0. Then in any case, if you have 1, you assume that this is the end of it. And then you accept. This path, whenever there is a 0, for example, or another one, this will die. Okay? That's natural. And then we try to amend it. Now the trick was that if we want, so this is an NFA which accepts all strings that ends with 1. That's it. So regardless of how many ones before you have, it will accept as long as you end up by 1. Now we say, okay, we will amend this a little bit so that when we get even, we will reject. When we get odd, we will accept. How we do that? We say, okay, we go back if we have another 1, and we need the 0 because we need to keep this alive. Otherwise, if we get any 0 here, we will be starting again from scratch, which is okay, which will be fine in our case. If you want to count odd number of ones in all of your string, not only at the end, then you need this 0. If you need only to count the end of the string, how many ones, then we don't need this 0. However, this is not working, and the proof was that when we converted to DFA, we actually designed a DFA which accepts all that ends with 1 still. So the same. Why is this the case? By analyzing a little bit, we say, okay, we don't need this one, but why? Why we don't need this one?
Accept even number of ones.
Yes, exactly. It's actually, it will keep things alive so that even when you have 1 here goes there back, the same one will make you go. At the same time, because you'll have 2 branches alive, both of them alive. So the one here will make you go there, and the one here will make you go to the second. And this will keep going. So what we need to do, just to remove this, the PDA would be something like, this is the start, this is the accept, for example. And if I have A, I will push A, and I will move to what? What is the general transition for any PDA? Epsilon. So what it means here? What?
You read an A.
You read an A.
Yeah, you pop an A and you push it up.
Okay. So here I'm reading from the stack always. So this is the stack, and this is the stack. Okay, both of them the stack. Here is the transition, normal transition. So I'm reading from my string here. So string is here, stack is there. So this is the top of the stack. And this is the character that you, or the symbol that you're changing in the top of the stack. So it means if I have my stack here, and I have on the top of my stack A, I don't care about here. If I provide, and I am in this state Q0, if I provided A, so the string would be looking like something like BA, whatever. If now I have A, and here in the stack I have A, I'll just pop this, replace it by epsilon, which is nothing. Yeah? If I decided to put here B, it means pop and replace it by B. If I decided, for example, to say no, actually I'll put epsilon and B, what it means, only push to the stack. So I don't care what is on the top of my stack. I am adding here, but this is epsilon, B. So I am pushing into my stack only. So with these two things, either you can replace on the top of the stack, or you can push, build, or you can pop. So replace, push, or pop. Depending on the symbol that you're reading here. Okay? Remember this. Fine. So let's have a look at conversion. So this is the general case of conversion. So you take your grammar, you say this is the start, this is the, so you build like, first you start by 3-state PDA. That's it, no more. No matter how many rules that you have in your context-free grammar. Okay, so even if you have like 10, 5, whatever, you only build now, start by 3 states. Q start, Q loop, Q accept. And then you say, in the Q loop, so always you transition from the Q start to the Q loop by epsilon, you push in the stack S dollar and S, which is the start variable of your context-free grammar. So always, because we have the start variable. Normally we call it S. You can call it anything else. It is where you start. So you have to push both of them. And then you loop here. Somehow, I'll just explain it now. But the importance is that you move also from Q loop to Q accept by just popping the S dollar from your stack, from the bottom of the stack. Because S dollar recognize the bottom of your stack. It means that you popped everything, nothing else left, and you finish. So I need here to mimic or to simulate the process of generating a string in a CFG, because in CFG you generate a string. In PDA or in other, you recognize it. But the problem here, I need then to simulate production through recognition. That is the trick. And I'm doing that by this loop. The loop says, okay, if you have any rule that looks like A to W, then what you should do, you should say, on epsilon, I will push and A, if in my stack is A, I'm going to replace it by W. And this is logical, because in context-free, how you produce, you replace this by W, the A by W. That's what you do, anyway. Yeah? You remember how you do production in CFG? Okay. So, any terminal in this case, I would replace this terminal by epsilon. Once I read it. Because this, it means that you're reading the string and you're matching it against what is in your stack, so you accept it or reject it. At the end, the idea is that I'll be able to pop all of my strings, all of the characters, the symbols in the stack, and in this case you have actually produced your string using your CFG. Okay? Kamal, would you please just move the slides a little bit down? Yeah, so now this is the difficulty that we run into. The difficulty is that sometimes we have complex rules. We have S. If we have the rule S give me X, Y, Z. How I'm going to do that in the loop? You replace that in the loop by the following. You say S give me Z. You start from the right. Remember, don't start by X and then Y and then Z. You need to make it upside down because you want to meet, when you produce in the other way around. Okay, so we have S, give us Z. If I read A, then that's it. You don't put A's anymore. All epsilon now. Epsilon give me Y, epsilon give me X. So you're pushing now after Z, you push Y, you push X. Because remember, in the stack, I'm pushing on the top of the stack. Once you read, you want to read it in the opposite way. That's why I replaced the XYZ by first put the Z on the bottom, then Y on top of it, then X on top of it. Because once you read X, then Y, then Z. Okay? Anyway, do it mechanically. Just do it like that. Remember how to do it. If I have X, Y, Z, you do Z first, Y then X. And you only have A at the start with the S, and then epsilon. Okay? You have to study this, right? You have to remember how to do it. Okay. Excuse me. Okay. So let's take an example from the lab, or let's take an example, a simple example, this one. S give us A, S, B, and epsilon. Right, so let's have a look. First of all, we said you need to start from a Q start. You go to Q loop, and then you go to Q accept. How I should move here from Q start to Q loop? What is my starting string? What is my start variable? S. So I need to, in case of Kamal, would you go up again? Up, no, yeah, here. So here you go. You have to, on epsilon, you push both S and S dollar. So this is always going to be the case. On epsilon, you push S, which is the start string, and then S dollar. So if I have here A, what should I do in this case? What you should push? A. And S dollar. Okay. And the transition to the accept is going to be what? On epsilon, if you read S dollar, then you finish all of your stack. So you pop it and you accept. And this is the case there. Okay, so now how we should loop? We go to the looping. Here I have the XYZ. What are the XYZ? They are A capital, and then B. So I'll just start by doing the same thing here. So on epsilon and A, I will push A. I will push what? A, B. But this is not complete. So this is your first step. And then we apply the next thing. Would you please also, Kamal, okay. Now, and also in the terminal stuff, we need also to place all the terminals that we have. What terminals here we have? So I need to say on A, if you have A in your stack, you pop. If you have B, and you have B in your stack, then pop. You need all of these. Not only, so you need to add these. Don't just look at your rules and then stop. You need these. Because you need a way to pop. What other rules I have? Well, in case of A, you go epsilon, which is fine. This is straightforward. So the only thing that I need to worry about is this, because it is complex. Here we have it's more than one character or one symbol. So what should I do? I'll just put it here. So we say that you need to have 3 stages. First, what is the conversion here? What we say, A, S, X, Y, Z. What we should do? So this is when we have, I'm moving from Q to R on X. Whenever I have A, I move from Q to R. And I have here in the stack S, then I need to replace it by X, Y, and Z. Okay, so what we should do here? You should tell me, guys. What we have here, the A here in our case is what? Is epsilon. So on epsilon, and I have A S, which is in our case is A, I need to place epsilon A Z, which is in this case B. So I have on epsilon here, this is the case, in our case it's epsilon, we don't have A. On epsilon, and you have what? You have A in your stack, then you need to replace it by B. Now the second thing, okay, on epsilon, epsilon, you move and add A. And epsilon, epsilon, you get what? A. Okay. That's it. And then we finish, we remove this. The rest is okay. Of course, here we need to add epsilon. So on epsilon, I have A, so we remove it by epsilon. Okay, so that's it. I converted this to PDA. Any questions?
How about if you have a B, capital A, B as well, as an option? So do you do the same thing on that?
What do you mean? You mean you have another rule?
Like you have in the gap.
Yeah, as many rules as you have, you do the same thing. Yeah. But remember, the significance of the start variable is that it takes you from Q start to Q loop. Once you're there, you add any. So for example, if I have OB and B give me say B, then you add here what? On the loop, anytime you have epsilon with the B, you replace it by B. That's it. Conversion to PDA, it's a bit involved, so you need to, stay alert and go back to those 2 pages that I used now to do the conversion, and use them a lot. This you need to practice. You'll forget in the exam if you don't practice. Definitely. So don't just look at it and say, yeah, I know how to do it. Knowing how to do it is different when you have the exam, you just forget, because those strings, the epsilon, and they will create a bit of confusion for you. So be careful and memorize these two steps of conversion. Okay, I guess that's enough for this. What time is it now? 20 minutes?
You have an example of PDA in the lecture notes, which doesn't seem correct.
Okay.
I'll keep looking at it. Pushing in here. If you go that way, you never put it.
Yeah, because here you have O.
And it has to be equal. So if there is a short
Right. Is what? Turing machine. Yes. Yes. But Turing machines, I explained in the lecture. Many of you maybe have not come to the lecture. They don't bother to come to the lecture. We said that Turing machine is actually, the question would be around the language accepted by Turing machine, the borders of the languages, and you will not be asked to design a Turing machine. Okay? So, and theorem, more or less, we covered them enough in the theory. So, yeah. Okay, do you want to do a little bit of O notation?
Yeah, definitely have questions.
Okay, let's do that. My advice is also go to the labs themselves and solve them again, because they cover everything. All of those labs that we provided with the questions and so on, they more or less cover the whole material. Second, go to the solution for the first assignment, because it contains also valuable resource. And we said we would put also the solution for assignment 2 once we once you get the marks, you'll also get the solutions for those. Because in the exam, we might ask you also about algorithms. So algorithms in terms of complexity of the algorithm and the algorithm itself. What is the best approach to solve a certain problem depending on its complexity? If it's intractable or it's NP complete, what you're gonna do? Normally, if n, the size of the input, is high, then good luck with the exhaustive search or exact methods, because it's going to be very, very costly. Normally, people don't do that. We just escape to some type of heuristics or inexact methods, such as the greedy, the grasp, and simulated annealing, genetic algorithms, all of these things. And you might as well would like to have a look at these and try to understand the logic and be able to write the pseudocode for these. Okay? So these I'm not going to cover again, because we covered them. You just need to go back and look at them, study them. If you need explanation, we can do that next week lab. Okay, let's do a little bit of O notation. All right. So 3n squared plus 75n plus 2015, because now we are 2015, not 2014, and it will make big difference. Would it not?
No.
Not at all. Big O for that. And you get big parts. Yes. So it is actually ON squared. Why? Because here we have a constant. Here we have n, which is less significant than the n squared. N squared is the most important stuff, and I don't care about the constants, multiplication. So at the end, this is ON squared. All right? 5 n 2040 plus 2 to the power n. This is nice one. O what in this case? What is the big O? O n. But this is n to the power 2014. So it's O of to the n to the power 2014. Yes? Yes? No. Completely no. Why? Which one is bigger? This and this, or this? They are, competing head to head. These two giants. This is a giant, although it looks benign, but it's just deceiving. That one. And n to the power of 2014. Which one is bigger? N or which one? 2 to the power n.
Yeah.
Well, yes, on the long run. After n is big enough. But at the start, this will be actually much bigger than this. Yeah? But once n grows really big, then this will beat to the n to the power 2040. So at start, you might see that when if this is n and this is O, you know, the complexity. So we're talking here about different, you know, terms. So you can see, for example, at the start, this will be actually, for example, maybe this will be n to the power 2040. And this would be 2 to the power n. I'm just trying here to, you know, but after certain value, if this is 2 to the power n, so you can see the, here is the values. So it starts, you know, lower than the n to the power. This is high. And then, so let me magnify this a little bit. So the same thing, the same x here, this is 2 to the power n, this is n to the power of 2014. Now, after certain value of n, we will be here, for example, and here you can see that indeed something like that. This is now the small n to the power of 2014, and this is now could be the 2 to the power n. So after certain value, it is actually more powerful. How I should know this value? Easy. You just make sure, you know, assume that they are equal. So you say equal n to the power of 2014, and then you solve the, you know, the equation. Okay, good. Do I need to solve this equation and say that all of that? No, you just mention it's all. I left the wrong answer. It's O 2 the power n. That's it. That's your answer. That is what requested from you.
Isn't 2 a constant?
2 is a constant. Yes, yes. But this is the exponential. This is the definition of exponential. You have always to the base here, you have a constant, and you have here the variable. So the variable on the top, not on the bottom. While here, it's the opposite. I have n in the bottom, which is the variable, and 2014 in the top. Which is, this is constant, and this is the variable. And you guys keep forgetting. If you have the variable on the top, it's a disaster. It's a complete disaster. This is the disaster. From algorithmic point of view, because complexity will be really hard. Yes, you want to yeah, so we say this is polynomial, no matter how big you have up, although it's just really big here in this case, but it's still polynomial code. And this is exponential. Because as I said, after a certain value of n, here, things start to change dramatically.
So the exponential, why do you keep 2? You could have just put O to the power n and ignore the...
2? No, you can't ignore the constant here because, you know, it's not multiplication, it's the base. As here also, you can't ignore the constant here because, you know, it makes difference between O n to the power 3 and n to the power 2. So no. Okay. Other questions? I mean, this is important because, you know, you need to get this right in your head. Let's have a look at another.
So if it's multiplication, do you correct the constant or not? Or do you leave it?
The multiplication, or do what?
If you've got like 75n.
75n.
Do you keep the 75?
No.
Or do you say just
No, ignore it. Strip it, like strip down the whole terms until you have n and here's something. Okay, or the opposite. Here's something and here's n.
Okay,
strip it down. Just completely ignore everything else. Okay, let's have a look at another one. So we have 214. I don't know, n log n. Okay. What we have? Which one is going to be more or faster? Which one is faster? N log n is faster. So, which one will make things, you know, grow faster than in this case and get the big O? Is it a constant by n or n log n? Yeah, see, it's, the big O here is actually n log n. Put it like that. Okay, keep it like that. Why? Because this is constant, I don't care about it. So n, which one is smaller, which one is bigger always? After a certain value also of n, log n will be bigger than 2014, of course, and then, of course, you have very big numbers. Okay, let's have a look at another one. So this is n log n. If we say n log n plus n squared, which one would be specifying the big O?
N log n.
Which one is bigger? N log n or n squared?
N log n.
Bigger? I'm gonna punish you hard. No, it's n squared, because remember n squared is n by n. So it comes to the to the question whether whether log n is bigger than n or not, because these just cancel each other. So which one is bigger, log n or n? N is bigger, of course, much bigger than log n. Log n, you try actually to shrink it down a lot, because log is opposite to the power, exponentiation. So this is bigger. Hence, the big O in this case is what? Good. Right. Same idea here. If I say n squared plus or n to the power of 3 log n, which one is bigger? What is the big O in this case?
Sorry? Squared.
NQ.
NQ. Yes. So we say O n to the power of 3. This is the big O. Right. Same logic here. This n to the power of 3 is actually this, yeah? And these will cancel each other. Which one is bigger, this or this? This. Then we say this is the big O. Good. Okay, now 2014, maybe it will be replaced by 2015 this year. Plus half n factorial. Let's have a look. What is the big O? Actually, let me put this. So we have 2014 here to the power of n plus half n factorial. Which one is bigger? What do you think, guys? I'll give you 2 minutes. Debate. Which one is bigger? Is it over?
N factorial.
Right. Oh, okay. No, I don't think there is. turn because 11.